Hello students, welcome to lecture of Kinematics and Theory of Machine. Myself Shailesh Patel, and we are going to continue our chapter Acceleration in Mechanism, and in this lecture we will solve the example which is based on acceleration. Okay, let's start. So as you can see on the screen the given data for the example. So PQRS is 4-bar chain with the link PS as a fixed and length of links are PQ is equal to 62.5 mm, QR is equal to 175 mm, RS is equal to 112.5 mm and PS is equal to 200 mm. The crank PQ rotate at 10 radian per second in the clockwise direction. Draw the velocity and acceleration diagram when angle QPS is a 60 and the Q and R lies on the same side of PS. Find the angular velocity and acceleration of link QR and RS. Okay, so let's check what is the given here. So first of all, take the given data, write the given data. Okay, so length of all the links are given and angular velocity of link or crank is given. Okay, so let's take the given data. So all given data, first of all we convert that into meter. So because that is given in a mm. So 62.5 will become 0.0625 meter. Okay, 175 mm QR will become 0.175 meter. Okay, now the angular velocity is given omega QP. You can see the crank PQ is rotating at a 10 radian per second in a clockwise direction. So omega QP will become 10 radian per second. Now as you know that here what is given, so first is a PQ is fixed. So you can say here this PQ link is fixed. I am drawing this diagram without any scale so you can understand very well. First, so this type of 4-bar is given PQ R S and this PS is fixed and PQ is rotating in a clockwise direction with 10 radian per second. Okay, and other data is your QPS is a 60. So QPS, this angle is given 60. So first of all we have to draw the configuration diagram. Whatever the dimension is given, assembly and orientation is given. So that's we draw first. Okay, so first of all we will draw this space diagram and take the some scale. So you can see here the scale we have taken 2 mm is equal to 1 mm. So how we can decide which scale is suitable for us? So whenever you have to choose any scale, first consider the smallest dimension and largest dimension, and according to that you can decide the scale. Okay, right now 200 mm, as you can see 200 mm and smallest is a 62 mm. So 2 mm is equal to 1 mm means this dimension you have to draw around 31 mm means 3 centimeter and this will be 100 mm. Okay, means 10 centimeter, which is a kind of suitable or we can draw in our notebook. Okay, so let's start and you will make this whole arrangement like this because angle is given 60 and PQRS. So now our space diagram is ready. Now before starting the any velocity diagram, as you know that first we have to find the any one velocity from mechanism. So there is always like omega or RPM will be given, so we can find the any velocity of any link in our mechanism. Okay, so you can see on a screen omega QP means one angular velocity is given, so we can find the velocity of that link very easily. Linear velocity is equal to angular velocity into length of that link. So we will find the linear velocity first. Okay, we will find the linear velocity of this link. Okay, so linear velocity of QP is equal to angular velocity into length, and length is given in meter. So we will find what we have find. We have find the velocity 0.625 meter per second. Now we can start the velocity diagram. For that, first of all we have to take any scale. So what scale we can take? 0.625 meter per second. So 0.625 meter per second, what scale we can take here? as you check here, 0.625 meter per second, which is very small number is there, so we have to take larger scale, so you can draw very easily. So we will take here 1 meter is equal to 100 mm. So this dimension will become 62.5 mm, around 6 centimeter, which is suitable for our drawing purpose. Okay, now let's start draw the velocity diagram. As you know the procedure of the velocity diagram, what we have to do, first take all the fixed point at a same point, please. Like you can see on the screen, P and S. So first P and S will be at a some origin. This is the origin point. Now we will draw our first vector, which is the perpendicular to PQ. Okay, and length will be, as you know that this is a given 0.625 and scale is a 100 mm. So we will draw the line here, which length will be 62.5 something. Okay, and this point you will find here is a Q, and this length is a 62.5. Okay, now as you know that we have the Q, we find the Q. Now we will find the R. Okay, now so we have to take the perpendicular to QR and perpendicular to RS. Okay, so let's take the first vector here, which will be the perpendicular to QR, but we don't know the magnitude. So what we will take, we will draw the line with an extra length like this. Okay, we don't know the length because magnitude is unknown, we know only the direction. Now perpendicular to RS. Okay, means this is the velocity of R with respect to S. So we will draw from the S here, and direction of this line will be perpendicular to, means in this direction we will draw the line here, but we don't know the magnitude, so we will draw like this. Okay, now the intersecting point of this will be denoted by R. Okay, and you can see here, this is the velocity diagram. This is the velocity diagram of this 4-bar chain mechanism. And here this will be, if I draw in this direction, velocity of R with respect to Q, and this is the velocity of R with respect to S. If you measure this distance, and you will find the velocity of R with respect to S and also Q. So this will be our velocity diagram, you can see on the screen. Now find the velocity of R with respect to S and Q. Okay, so if you measure this distance, you will find this is the 33 mm. And as you know that we have taken the scale, here, which is a 1 meter per second is equal to 100 mm. Now we will find the velocity of R with respect to S, VRS, and you can find from measuring the vector SR and dividing by 100. Okay, now we can find the angular velocity omega RS and omega RQ by velocity of RQ divided by RQ and velocity of R with respect to S divided by SR. Okay, so this is the angular velocity we have find it here. Okay, so this is the half portion we have completed. Now we are going to find the acceleration diagram. For the acceleration, as you know that velocity of every element in a mechanism is necessary, so we will use this velocity. These three velocity will be very important. If you make any mistake during the finding this velocity, your acceleration will be wrong. Okay, so we will use this velocity in a further example. Let's find the acceleration. So as you can see, this is the given data from the example and velocity we have find it. Now for acceleration, as you know that we have to make table. In table, first is a link, second is a length of these links, and third is a velocity of link. Okay, let's check this. We have the three links which are moving, PQ, okay, PQ, QR and RS. And as you know, the velocity means length of that link is given in a given data. So we will put that value here, the length of these links. Okay, Then the velocity we have already find it 426, 0.33 and 0.625. So this velocity we have put it here. Now the most important points of this example is a radial component and tangential component. Let's find the radial and tangential component. So as you know that radial component is a velocity square divided by length of the link. So we have already found the velocity and length. So we will find the radial component of all three links. Okay. Now tangential component. This crank PQ is rotating with a uniform speed. So you can see tangential component will be 0 because uniform velocity is given. Okay. Or alpha is not given. When the alpha is not given, angular acceleration is not given, we will take the tangential component of crank is equal to 0. But any other element which are not rotating, pure rotation is not there, then there will be tangential component. But we don't know the magnitude right now, so we only know the direction, which is the perpendicular to link, and this will help us in calculating the example. So we will take the perpendicular of large length because we don't know the length right now, but when this type of two perpendicular will intersect, they will give us a correct position of that point. Okay. First we have to decide the scale. Okay. So as you can see on a screen, 0.625, 0.634 and 1.6. So our scale should be suitable for all these three dimensions. Largest is a 6.2 and smallest is a 0.634. So our scale will be 1 meter per second square is equal to 10 mm. Okay, I know this smallest component will be very small, but with respect to this larger scale, we have to take this scale 1 meter per second square is equal to 10 mm. Okay, let's start. As you know that first of all we have to take the fixed point. Okay, fixed point. Which are the fixed point in a figure? You can see P and S. So we will take P dash and S dash. Okay. Now you know that this crank PQ has no tangential component. So only radial component give us the final acceleration of Q with respect to this P. So we will take the radial component of 0.625. Okay. So it will become 62 mm in direction of, you know the direction of link from Q to P side. So we will draw this type of first radial component and it will give here the Q dash. Okay, this will be Q dash. Now with respect to Q, let's take the R. So acceleration of R with respect to Q, we know the radial component 0.634. So what will be the direction? As you know that direction will be in a parallel to link. So it will be in this direction. Okay, in this direction. But this length is totally depend upon the radial component, which is a 0.634. So it will be very small, like here you can see this is the radial component, like this. Now from this point, let's take this point as a X. From this point we will draw the perpendicular. To this line link QR, but we don't know the magnitude. As you can see here, magnitude is unknown, but we know the direction is perpendicular to link. So we will draw the perpendicular, means this perpendicular here, and we don't know the direction length of this link, so we'll draw in a like this. Okay, as you know that is R is also, this R is also connected to S, and we know the radial component of R with respect to S. So we will draw the radial component now. Let's draw the radial component. Okay, as you know that radial component is always parallel to link in this direction from R to S. So parallel to link, and value depend upon this magnitude is a 1.6. So this is the direction and value. So this point we can denote it as a y because it is an intermediate point. This is not the final point, it is a radial component. Now from this point we will take the tangential component, which is the always link, perpendicular to link. Okay, now draw the perpendicular to link here, but we don't know the magnitude, we know the only direction. So I have taken the length is a extra. So this intersecting point, what we have done here, with respect to q we have taken radial and tangential component, and with respect to s we have taken radial and component, and this intersecting point here which give us this r point. Now I can say here this is the r dash. Now we can erase the extra length from figure. Okay, so as you can see in a screen, check this, you know this is the radial component, this is the tangential. So resultant, this will be the final acceleration, this will be acceleration of r with respect to q. Okay, and same you can see this is the final acceleration because it is a resultant of this is the radial component. Okay, and this is the tangential component, and this will give us final acceleration of r with respect to s. Okay, same as you can see this is the tangential component and this is the radial component. That's how radial and tangential give us the final resultant acceleration. Okay, let's check this figure. So what we have done here, I will quick revise here. So how we can draw this? First make this radial component here from this given data. There is no other tangential component is there, so this will be the final acceleration. Now what we have done, the radial component and then tangential component of extra length, because we don't know the magnitude. You can see here we don't know the magnitude. Okay, then what we will do, radial component of r with respect to s, and then extra length and perpendicular from, okay, for perpendicular tangential component. This will give us here r dash. So up to this point you can see on a screen we have finded the acceleration diagram. Now we require the angular acceleration of qr and rs. So how we can find that? First of all we have to find angular acceleration of qr, and for that we have to find the tangential component. We have to find these values. So for that we will measure the length of all tangential component. And as you know that this tangential component is equal to angular acceleration into length of link. So from this we will find this alpha. Okay, let's check this. So alpha is equal to tangential component divided by qr. We will measure this r dash y here, or you can check x r dash here, and you will find the value of angular acceleration. Same as we will do for the rs. You know that, check this, angular acceleration of r with respect to s will be tangential component divided by length of that link. So we will measure this tangential component here and divide by length of that link, so we will find the answer. Okay, thank you.